while we're doing the half a minute waited out before we start class today. But any questions at the moment, folks? Okay. Well, I think we can start officially. Welcome back, everyone. So today's class, our whole goal is just to finish off section 3.9. I want to do enough of the examples on that document so that we're in great shape for the homework problems that were indicated down here. I think we're in pretty good track for getting to all those. Any problem that we don't finish off today, I'll make sure we do post the solution. So if you're curious about the problem or you just want an extra example to take a look at that's worked through, each one of these will be solved. Well, we have our assignment 7. It's only those 2 sections. Our assignment for the moment is 6 that's due today. I also want to mention, since probably most of us are thinking about the upcoming exam 2 on Monday, if you decided you want to just focus primarily on these sections right here, because 3.8, 3.9 aren't actually on exam 2, that would be okay. I'm going to give a blanket extension to the entire class. I'm going to also change this date to reflect it after the exam, but I will accept it for full credit on Monday, October 16th. So if you decide to focus on these sections below here and then switch gears to these after the exam, that's not a bad strategy in all honesty. I mean, the best thing is to always be 100% caught up at every single point of the course, but that's not how real life works. So that's the reason for that extension there. Any other questions so far? Okay, and I guess the other announcements are really this is the same kind of stuff that we were talked about on exam 1. Only thing that's changed is it's exam 2 and it's different sections, different date. But it's definitely worth reminding, when you go to your second exam, some folks didn't have their sheet of notes, and that's totally okay. If you feel confident that you're going to rock this exam without notes, no worries. But everyone in the class is allowed a page of notes of this size, front and back, with whatever you would like on it. And I would encourage to definitely start working on that sooner than later. The sooner you have this put together, it'll also make studying these sections way easier as well. That's a really great first move, I'd say. Then when you come to the exam, you'll be allowed any kind of pencil, utensil, erasers, your single page of notes, and any calculator that's essentially not a graphing calculator. So as long as it's something like the TI-30XA, TI-30X2S, just like on exam 1, I'll be very happy with that calculator. But if it has a screen about this big, or if it connects to the internet, or if it says CAS on it, meaning it's a computer algebra system, those are the kinds of calculators that would be excluded. Well, any last questions, folks, about any of the announcements? Okay, I provided this document here just to study for the exam problems. All it is really a sort of test bank of what are the good questions from here all the way out to here. Some of them do get a little bit harder, some of them are involved, but keep in mind that on those harder questions, I can't ask really involved type of stuff on a real exam. Those longer questions are really more for practice more than anything else. The real exam is going to be like the last one. It's designed to be 67 minutes in length. We'll call it 75 since that's a nicer, rounder number. But it's really going to be shorter so it fits in a 60-minute time frame with time built in for you to check your work and that kind of thing. Well, that's my whole spiel. Any last questions or comments, folks, before we go back to 3.9? Okay, let's jump right in then. This is the problem that we solved when we were at the last class on Wednesday night. And I brought this up first since one thing to always keep in mind when you're looking at these kinds of problems is we had a positive derivative for the y-coordinate. That meant the y-coordinate had to go in the positive direction, meaning it was going up. That's what forced the x-coordinate to go left. So we wrote that there. We also know if we're talking about, say, dx dt, here it is way down on the bottom, that's going to be the rate of change of the x-coordinate. It's negative because if we look back up here, it was moving over to the left. So when you think of derivatives, think of the directionalities as well. And that's one major takeaway with these kinds of problems here. Were there any questions, folks, about getting through this one, or should we jump to example 2? Okay, let's take a look at just what happens on example 2. Examples 1 and examples 2 are pretty nice because they supply the formulas for us. So what's happening here is we're dealing with Boyle's law. At first, they give us a write-up of what's going on. It says on this first paragraph, Boyle's law states that when a sample of gas is compressed at constant temperature, the pressure P and volume V satisfies the equation pressure times volume equals C, some constant there. Now they go on to tell us, suppose that at a certain instant, the volume is 600 cubic centimeters, the pressure is 150 kilopascals, and the pressure is increasing at a rate of 20 kilopascals per minute. At what rate is the volume decreasing at this instant? So that's the whole question. And to me, this would be a terrible exam question in all honesty. It's awesome for homework. This is more of an exam 3 material. But what makes this hard is there's just a lot to kind of pull out of this. Here's how we probably would want to start. Let's put down all the given information. At a certain instant, they didn't tell us the time on this. And so one strategy we can write is at time t equals t naught. So that will be our certain instant of time that we're referring to when we go through this problem. It says volume is 600 cubic centimeters. So let's write out volume at time t naught, 600 centimeters cubed. The pressure is 150 kilopascals. So we can write here, pressure is also a function. So function notation, just like with V, could be used. Pressure at time t naught, 150 kilopascals. And here's the next statement. And the pressure is increasing at a rate of 20 kilopascals per minute. That last statement is a derivative. So let's write it out in this way. At a certain instant, that's the time t naught, the rate of change of pressure, I should highlight this as well. So that'll be dP with respect to time, so dt. This is evaluated at time equals t naught, so a little bit too early for those equality symbols. It says right here, increasing. Now, I wouldn't normally do this, but this is good emphasis to put in. If they tell us the pressure is increasing, think positive value right here. If they said decreasing, then we must put in a negative sign. And it's at a rate of 20 kilopascals per minute. So that's our entire write-up of this given information on that second sentence. Now, right here, it says, at what rate is the volume decreasing at this instant? So that's the question. Let's put here, we want to find, it asks for a rate, so this will be the rate of volume with respect to time. At this instant, this is time t naught once again. So once we find that quantity, we're all set. We will now be completed with the problem. Any questions, folks, with the organization phase of this information? Okay, so to me, the reason this makes kind of a bad exam question is there's really a lot to organize and put together. What I would think is a great exam question for related rates on the third exam, something more along these lines, where we have the function, we have the information, we can start differentiating immediately. That tends to work out a little bit better on an exam setting. So now for this one, well, if we want to find dV dt, we need to differentiate something, but that's where this comes into play. We have the equation from Boyle's law, which is the equation that says pressure times volume equals C. And even told us right away, C is constant. So that's the thing we're going to be dealing with right here. Actually, I want to move it slightly up on the page just to make sure to fit everything. So pressure times volume is a constant through Boyle's law. If we want to find dV dt, well, we need to differentiate this whole thing. But like in the prior problem, the variable p and the variable v, they're not just variables. They change with time. That's why there's a derivative dp dt. We have that p is some function of time. Volume is some other function of time. And so now when we go to take the derivative, here's how it's going to be set up. It'll be the derivative with respect to time of p times v equals the derivative with respect to time of the constant. A constant is just gone. We're differentiating a constant, sending it off to a zero. But over here on the left, we have to be extra careful. Anyone spot what the rule should be on differentiating this? Good call. This one will turn into the product rule. We're taking two functions of a variable time, multiplying it to each other. So product rule says this. I'm going to differentiate the first function, p. Because I'm using Leibniz notation, I want to write v first, just to be careful. V times dp dt. So what I've done is I've copied v and differentiated p. In the product rule, we throw in a plus. This time we'll copy down p and differentiate the volume function. So this turns into dv dt. And the whole thing equals 0. So that's not too bad. We have a formula right away after differentiating. dv dt emerges, so we should be able to solve for this right here. So let's do, in fact, that right now. Let's solve for dv dt and see what quantity we get. We can subtract volume times dp dt from both sides. So pressure times the rate of change of volume with respect to time is now negative volume times the rate of change of pressure with respect to time. Finally, divide by p, and we have the derivative we want completely isolated on the left-hand side. It's now equal to the ratio of negative volume divided by pressure times the rate of change of pressure with respect to time. Pretty weird derivative. So in Boyle's law, it was a really pretty fast-looking equation. But if we want the derivative of volume with respect to time, it kind of got convoluted down the line, all because of the product rule, really. Well, any questions at all, folks, on running through the product rule and getting that derivative? Okay, really, I'd say the trickiest step is right here, where we went and used the product rule. But now that we have this, we are extremely close to done. Recall, this is not what we wanted. What we wanted is the output when we input T naught into that result. So let's do this, just that. I'll put here, therefore, the rate of change of volume with respect to time is going to be equal to, oh, and I forgot my evaluation. Sorry, one last try. dV dt evaluated at time t equals T naught. So we're talking about a specific time instant once again. We're going to go negative V naught, or excuse me, negative V of T naught. Grabbed the wrong color. Oh, that was green. So negative V of T naught would go here. It's divided by pressure at time T naught. And it's still multiplying this derivative right here, dp dt. So it'll be times dp dt, also evaluated at time equals T naught. So now we're just going to plug in all those particular values. On the next step, it's equal to negative 600 cubic centimeters. Then we divide that by P of T naught, which is 150 kilopascals. Multiply that whole result by dp dt. That's 20 kilopascals per minute. That kilopascals right here is going to cancel the kilopascals from the denominator. we'll have centimeters cubed up above per minute as our overall unit on this. As it should be, the unit for V here is centimeters cubed, and the unit for time is per minutes. So that's what our unit should resolve to. We just need to take this 20 and throw it in right here. So negative 600 divided by 150 times 20. This is why we need a calculator for exams, but I did make this comment before. The calculator is kind of more of a comfort. It's not a major tool in the exam. If you left this as an exam question, if it was one, just like that, I'd be okay with that. That's the right calculus. That's the right algebra, the substitutions. But let's actually get the value out just to see what it's going to look like. So it's going to be negative 600 divided by 150 times 20. We get negative 80 exactly. So this will turn into negative 80 in units of centimeters cubed per minute. And I'll put this in a box since my work. I try to keep it linear, but it really spreads out for these kinds of problems. Well, any questions, folks, on the conclusion of that derivative there? Okay, I do have a question for folks because every time you do an applied problem like this, we need to be very careful about the sign of the derivative. They told us pressure is increasing in this problem, and so we had a positive derivative right here. Our derivative for volume is negative, and if we can't mentally decide that's appropriate, that it should be negative, we may have a problem here. So, any volunteers for an explanation of why it should be negative? Yeah, go ahead.
The pressure increases, the volume should decrease.
Exactly. That's essentially what's happening here. In Boyle's law, we increased pressure of that sample of gas, and just like you said, its volume footprint should now shrink as well. And that's what we're seeing here because of that negative sign. Volume is decreasing at that time instant. We still don't even know what time T naught is, and you don't always have to specify this. But if you feel like you're plugging in something like T and we don't know what T is, occasionally people put in a T naught just as a placeholder. But we did it, folks. That's the conclusion of this one right here. Does it make sense to folks on how we navigated through this information? Awesome. Again, what I like about this problem is they supplied the actual function we differentiated immediately. Pressure times volume equals a constant, but still kind of hairy for an exam situation because there's a lot of details flying around. But let's try off our next problem then. In our next problem, this is a situation where we have no function. These to me are the challenging ones. We have to devise what is the function in the first place that we have to differentiate, then differentiate it and go through the motions. There's problems very similar to these first three of problems that we've done so far in the homework assignment. Then when we go beyond these, the next two are kind of optional. So as we're solving this one, let's decide if we want to do something from physics again. So this is about general relativity once more. Or if our final problem should be something about combustion engines. So whichever one you think seems more interesting, we'll give it a try. But first, we really ought to do this one to support the homework. So here's the scenario. It says, two people start from the same point. One walks east 3 miles per hour, the other walks south 2 miles per hour. How fast is the distance between the people changing after 2 hours? This is like one of those terrible math problems that people like to joke about, where one train leaves LA at 5 o'clock, another train leaves New York at 6 o'clock. When do they meet? Something like that. But this one's worse. And what makes it worse is exactly, they're going in different directions. They're 90 degrees apart, right? Exactly. So if you found that it's really a triangle, Pythagoras theorem is what's giving us the formula. Good call. So it's a nasty problem, but without organization, it kind of falls into place. So two people start at the same point. Here it is. That's the same point right there. Actually, want to kind of make sure we use this space to our advantage. I'll put it up here. One walks east 3 miles per hour. I'll just indicate it this way. The other goes south at 2 miles per hour. make this a little bit shorter. This person's going a little bit slower. We want to know how fast is the distance between the people changing after 2 hours? Well, we have this right here that we can call the distance if we would like. And although you could use a variable for d for distance, that could be awkward because we're going to be writing things like dx dt. We wouldn't want to write d dt because that gets really confusing. So we could just use something else generic like z. Why not? This one can be an x, and this one can be a y. So we have 3 variables all representing length. Person going east has this length, x units in miles. Yeah, that would be miles. Y miles going this way, and z miles going that way. Then, like you mentioned, this is a Pythagoras theorem problem. We're very interested in the distance. That means we're very interested in z, distance between the 2 people. Pythagoras theorem tells us that z squared is going to be equal to x squared plus y squared. So that's our fundamental equation that we have to use. Now it's just like the Boyle's law problem in a certain sense. Once we have the formula, we're just going to work with this directly. But now we need to be careful. The one walking east is doing 3 miles per hour, so that's a function of time. The one going south is doing 2 miles per hour, so y is a function of time. And if these lengths change with time, so does z. So the situation here is that x is a function of time, y is a different function of time, so I'll call it g of t, and the distance between z is yet a different function of time. You could call that, say, h of t. The reason I put these down is to help differentiate this thing. We're going to need to use Leibniz notation to be careful, but it's also going to be chain rule because right where you see x squared, there are really 2 functions. The outer function is the power 2 function right here, and the inner function is x right there. Well, we now need to differentiate. Any questions so far, folks, before we just smack it with a derivative? Okay, so differentiate with respect to time. If they ask how fast, that's a derivative. But if they ask how fast with the time component, it's a derivative that does this. D dt. We'll differentiate the left-hand side, which is z squared. Differentiate the right-hand side with respect to time, which is x squared plus y squared. Now let's take a look at the z squared once again. This is all differentiation implicitly, but that's just a weird way we're using chain rule. In the chain rule, like we indicated earlier, the squaring function power 2, this one is the outer function. We'll handle first. The inner function of z, which changes with time, so we'll call that 2 for inner. Now here's what it looks like when we differentiate. First 2 will come down. The new power is going to be a 1, so I'll leave it blank there. And then we multiply by the derivative with respect to time. So that's how the chain rule goes essentially each and every time. Inside here, we'll throw in a z and a z here as well. Only that this time, dz dt is going to stay exactly where it is. We can't differentiate it because we don't know the function h of t necessarily. So that's the entire left-hand side. Differentiate z squared, you get 2z times the derivative of z with respect to time. Yeah, go ahead. The right here you're saying?
No.
Up above? Oh, right here. Oh, it's mainly because of the chain rule. Just for a really quick example of kind of that issue there. If we had a function that went y equals, let's say, maybe it's, what's a good function? How about x plus 3 to power 2? So if we differentiate that, we'd go y prime. The outer function is 2, so 2 would come down. The new power is 1. We'll put it in this time just because we can. Then we would multiply by a derivative. I use prime notation here, so I'll use prime here. And the inner function, the x plus 3, copies in both locations. So the answer to that question is, the reason it's not squared is the inner function directly copies inside here. And over here, we're just taking the derivative of the inner function z itself, much like what happens in this pattern of attack. Does that make sense, seeing this analogy over here? Gotcha. Other questions so far? Okay, to me, these derivatives are always strange because they just look strange, right? But if you can put down an analogy that kind of matches the situation, sometimes that's a good strategy of getting through the problem. Okay, well, we've got the left-hand side. Let's do it again on the right-hand side. It's the same thing, right? All we did is change the variable name, so it's going to work out exactly as before. Differentiate x squared when x varies with time. You'll get 2x, but then you multiply by dx dt. Essentially, that's what we have here, 2z multiplying by dz dt. I put parentheses just to show the pattern more than anything. But at the end of the day, it's just going to look like that. Differentiate your y squared, and you get plus 2y times dy dt. So we've got it, folks. That's our full derivative here. We want to know how fast is the distance between the people changing after 2 hours. So that means we want to find the rate of change of z, because that's the distance between them, with respect to time, evaluated when time equals 2 hours. So for us, we're solving for this, dz dt, and then we'll input 2 hours into that and see what it all turns out as. But because we're solving an equation, you can simplify your life a little bit. 2 is a factor on all terms. Just divide the whole equation by 2. You'll obtain z dz dt equals x dx dt plus y dy dt. So that's our result there. Finally, divide the whole thing by z. That's appropriate. Z can't be 0 because we're interested in 2 hours after. There's an actual positive distance at 2 hours. So with z not being 0, dz dt is solved for. The moment we write that it's equal to, I'll take 1 over z, dividing this out, multiplying x dx dt plus y dy dt. So that's not our answer, right? Because we have to plug in 2 hours, but we're in really good shape. So this is where it settles so far. Now we have to go and look for values. We actually know what dx dt is. If we look here, x is the one going east, and he walks at a rate of 3 miles per hour. You know dy dt, that was the rate at 2 miles per hour likewise. What we don't know is, we don't know z, we don't know x, and we don't know y. But we can solve for those. Let's just say this triangle can become a whole new diagram with values filled in at a time t equals 2 hours. So at time is 2 hours, here's what it looks like now. We had x here before, but we'll fill it in. We'll fill in y, and we'll even fill in z as well. I wish I had more colors. That's kind of hard to color code all these different objects. But let's go back to here. This is a value x. X is increasing at a rate of 3 miles per hour, and we're looking at 2 hours later. You can see what the distance should be right here. Exactly, it should just be 6 miles altogether. Likewise, we're moving downwards at 2 miles per hour, so y is now 4 miles per hour. I'll just write 4, I didn't save enough space for the unit. And for z, well, here's our formula. Pythagorean's theorem was useful to find the derivative. That's also useful for solving for z. So let's just write it out again. Z squared is going to be x squared. So that's the 6 squared plus y squared. That'll be the 4 squared in our diagram. So z squared is going to be 36 plus 16, which is something like 46, 52. We can now take the square root and take z equals, automatically it's plus and minus when you square root this. But in this applied problem, z is only positive. So we get away with just writing root 52. And 52 factors, I think this is something like 4 times 13. So we can reduce the root to 2 root 13. This is more of a quality of life step right here, not required. If you left it as root 52, I'm totally fine with that. But sometimes reducing the root can make the rest of the problem a little bit nicer. So that's the only reason I took the trouble for this one. So we have a value for z. It's, I guess we could fill it in here, 2 root 13 miles. We have a value for y and we have a value for x. So they're all going to be substituted in that way. Then for the other values, I have one last color I can use, dx dt, dy dt, come from here and here. So last thing to do is plug everything back into this equation. Really, that's the same thing we did with Boyle's law and even example 1. So these problems at least have a definite kind of organization to them. They always kind of go the same way. So last step, dz dt. Before we calculate it, are we expecting a positive quantity or a negative quantity on this one? Absolutely, it ought to be positive because the distance z is increasing. And we'll see at what rate it actually increases when we fill all this in. So good call, we have a positive quantity here. So first it's going to be 1 over z becomes 1 over 2 root 13 from our work on the right. The value of x, we're still looking at the work on the right, is 6 miles. So I'll throw a 6 here. dx dt, when we go back up to the top, is 3 miles per hour. So I'll go times 3 here. Then plus, the y value is 4 miles. And dy dt was 2 miles per hour. So times 2 goes right here. Last thing to do is we'll just simplify this as much as it simplifies reasonably. This turns into, I'll put 2 root 13 down in the denominator. In the numerator, it'll be 18 plus 8. So now we have 26, 2 root 13s. So that reduces, we can divide 2 into 26 to get 13 over root 13. And that's a pretty fine answer at that step. In fact, if you put it in the calculator right where the red dot is, that's always okay as well. But this kind of stuff is good practice. It can come up in surprising ways. So let's keep simplifying it. Sorry, say again? Exactly. If we multiply by root 13 over root 13, something else happens. We have 13 root 13. The denominator root 13 times root 13 is 13, allowing our 13s to now cancel. And so the whole thing is root 13. But what are the units on this thing? Well, z is in units of miles per, t was in units of hours. So this one came out exactly as root 13 miles per hour is the rate at which this guy, z, is increasing, the distance between the two people moving. But it's not always root 13 hours. It only takes on that value specifically when they've been marching away east and south at those speeds at exactly 2 hours. At exactly 2 hours, that's the rate at which their distance between each other is increasing. Well, we did it, folks. This one's kind of nasty. It's really a bad one for an exam setting. If it was on exam 3, I would probably have an exam with 4 questions because it takes a while to put all that together. This is more of a homework type of a problem. Any questions or comments on getting through it? Okay, well, let's see how much time we have left on our next ones. We can either do this one that came from the theory of general relativity. We actually differentiated this once before when we were looking at the force function in a prior section. Or we can take a look at what's happening with law of cosines and this thing right here. Any volunteers for a direction to go for our next problem? This one right here? Okay, let's give this a try. It's got a picture, so I like that about it. And honestly, what's happening with example 5 is extremely close to what's happening with example 3. Here's the difference though. What we really loved about example 3 is the 90-degree angle right there. We're losing that on our current example, the one we decided to choose. So if you don't have a 90-degree angle, the formula still sort of looks like this, but then you take -2 times x times y times cosine, whatever the angle theta is right there. So we have to adapt this formula by using law of cosines. And that's what this diagram is saying right here. First, let's pause on law of cosines. There's 3 formulas here, but there's really one overall formula. It's the pattern and how you deal with it. So if we focus on beta, then we need to look at its opposite side, which is b, and deal with the a and the c. So this is typically how we think of law of cosines. We want to focus on the angle beta and the side opposite of it, b. This turns into b squared equals, I want to color code that, so let me try again. We take the other sides, a squared plus c squared. So at that stage, it looks like Pythagorean's theorem, but because beta is not necessarily 90 degrees, we'll go minus 2 times a times c times cosine of beta. So that's essentially what the law of cosines is trying to say altogether. Now, beta is 90 degrees, pi over 2. Cosine at pi over 2 goes to 0, and you just get back this portion, Pythagorean's theorem itself. But if it's not 90 degrees, you just have to deal with this corrective factor to get the right values out. Any questions, folks, about the law of cosines there? Okay, so to get through our current problem, this is where we're getting our formula at. We're not using Pythagorean's theorem, we're just using its extension. And now we have to take a look at this problem. So what in the world is going on here? It says, in the engine shown in the figure below, we have a 7-inch connecting rod fastened to a crank of radius 3 inches. So the connecting rod is this one right here. The crank is from the center to here where the connecting rod links up. It tells us next, the crankshaft rotates at a constant rate of 200 revolutions per minute. That's extremely fast, but it's an engine. We should expect some really fast speeds on this derivative this time. So the numbers are going to look large, but that's okay. So 200 revolutions per minute, what they mean is this dot is moving like that 200 times every single minute. Now it says, find the velocity of the piston. So we're doing a velocity problem when theta, they indicated it right here, is pi over 3. When they say velocity of the piston, well, the piston is moving either this way or this way. We'll find out which way it's going, and we'll also find out at what speed it's going that way. If it's moving to the left, I'm expecting a negative derivative, because that means this length from here to the piston is getting shorter. If it's moving to the right, I'm expecting a positive derivative, because then that length would be larger. But the nasty thing about this problem is we don't necessarily want to look at an engine diagram. Unless you're an expert on this kind of thing, I definitely am not. So here's what you want to do to solve this problem. The most important skill in any applied setting like this is completely abstract away from the diagram. The diagram has too much mental noise. I can't solve the problem there at all. Instead, this is what we'll do. There is a triangle there, so we're going to take what's a real engine and abstract completely away to this. Trying to draw the triangle roughly the same. Doesn't have to be perfect, but that'll do the job. Now we do have some information here where they indicated the theta is for this vertice right here. So let's throw in our theta value. So we've got a theta. We also have a 7-inch connecting rod. Well, where's the 7-inch connecting rod go? They said right here, the connecting rod is this portion right here. So our abstraction, it would go in this location. So we have a 7-inch connecting rod going that way. It's fastened to a crank of radius 3 inches. So radius is helpful. That's here to here. Well, maybe not super helpful. I would still probably want to use, it's fastened to a crank. So you find the crankshaft. This length right here is the 3 inches. So we have several things all together here. We have a theta, we have 2 side lengths. These side lengths will never change in this problem. But the side length that does change is the very bottom. This length is the most important one. It corresponds to this length in the diagram from the piston all the way to this center of the crankshaft arm where it emanates from. So we need to call that something. That's the thing that's changing. It should be a variable. So how about X? X would do the job. That would be X inches. I'm sensing the need for extra space, so let's drop this down below. So we've done it, folks. That's the entire diagram. But let's see what they're asking once again. Find the velocity of the piston when theta equals pi/3. That's a tough question. They're asking, we want to find the rate of change of x with respect to time when theta equals pi/3. I agree with you on that. Good call. Let's take another look at this and see if we can determine the sign. So when it says it's, let's see, it's rotating counterclockwise, that means this arm is going like that, rotating that way. So if it rotates in that counterclockwise, this is going to start moving to the left. So that means our x is actually shrinking as this rotates to the right. Does that make sense to folks? Awesome. If I was a good artist, I'd probably try to draw it this way. This dot can rotate here. Oh, this is already coming out bad. That would cause this arm to move. Let's see here. Oh, that's really hard for me to draw. Maybe it's better to just kind of point at it. It's really difficult to draw on this thing. But if that moves in a clockwise way, it carries the piston with it to the left, meaning x is shrinking, and so we're expecting negative. We expect dx dt to be a negative quantity. Its units are going to be in, let's see, inches per minute. There's minutes in this problem. And that's what makes this derivative awkward. It's dx dt we're evaluating when theta is pi/3. And I didn't even use an evaluation bar here. I cannot say this, so please don't write this down. It would be incorrect. I can't do that. Reason being is dx dt accepts a time. It doesn't accept an angle theta. So we're kind of stuck on that, but we can still describe what we want. We want the value of the derivative specifically when theta itself takes on pi/3. So that's kind of a strange problem so far. Now we need to start finding quantities. We don't even have a formula to differentiate yet, but let's look at again at some of this information. We have a 7-inch arm here, 3-inch arm there. Those never change in this engine or else the whole thing breaks. But we do know the crankshaft rotates clockwise at a constant rate of 200 revolutions per minute. Or sorry, yes, counterclockwise. That would probably break the engine as well if it went the wrong way. So let's see what that is saying. So d theta is what we're talking about. The rotation of the crankshaft is relative to theta now. The rate of change of theta with respect to time, if it's 200 revolutions per minute, Well, let's think of a trig table. In a trigonometry table, or a unit circle, right here, we start at 0 radians. In 1 revolution, we'd come out around and rotate by a value of 2 pi altogether. That's going all the way around once and stopping right here for 1 revolution. This thing's doing 200 revolutions per minute. So in 1 minute, the rate of change of the angle theta would be 200 revolutions multiplied by 2 pi radians, all right, rad for the unit radians, per minute. So it's going to be 400 pi radians per minute altogether. So we have a rate of change. And how do we know it was a rate? They said right here. If they tell us a rate in this kind of way, then we're expecting a derivative. The derivative is with respect to time. And so that's, to me, one of the tricky things about this problem. Even without the law of cosines, I think this is really tough to come up with. Does it make sense, though, on how we put that together there? Okay, so we have 400 pi radians per minute is what's happening with that crankshaft. So it's really flying, but it's an engine. We should expect it. Next thing we need to have any chance of this problem is we need a formula, right? So essentially where example 5 sits is exactly to this step right here of example 3. We need to produce that formula right there in order to have something to differentiate and walk through the rest of the problem. So let's go and put it in. We'll need the law of cosines, but our law of cosines is going to be relative to theta and the 7 inches. So here's how it comes together. We can say 7 squared, that's the side opposite to theta, will be equal to, grab the other 2 adjacent sides around theta, 3 squared plus, this is x dash inches. I think that's a little awkward with a dash there. Let me just take that off. 3 squared plus x squared will be equal to -2. Go back to the adjacent sides again, 3. Oh, sorry, I made a mistake here. It's -2 like that. I'm not sure why I put an equal sign. Must have been micro sleeping at the moment. So -2 times this side 3, this side x, times the cosine of that interior angle theta. So that's pretty much the pattern for law of cosines on this thing. Any questions at all, folks, on getting to that stage? Okay, well, we could differentiate it right here, but I think this is a good one to try to simplify first. If we have to differentiate it, it's always nice if it's just cleaned up a little bit. This becomes 49 equals 9 plus x squared. Over here, it just turns into a -6x cosine theta. And finally, we're going to differentiate that whole thing with respect to time. Any questions first before we begin?
Would we not put theta in?
We could actually at this stage, and in fact, we do have to at some point.
Yeah.
So it kind of just depends on what we want to do.
So like that'd be easier because like cosine theta, well, 2/3 pi. Oh, it's just pi.
Yeah, that will actually be a nice value. Exactly, that will turn into a 1/2. Yeah, let's do that, those evaluations right here and now. So we can say here, when theta equals pi/3, what I'm going to do now is carry this equation over. I'll put a little orange line to just signify that. We're going to be getting that 49 equals 9 plus x squared minus 6x cosine pi/3. And like you said, cosine pi/3 is a nice value. It's exactly 1/2. So visualize a 1/2 going in here. Our new equation is that 49. Guess we could subtract 9 for both sides, but let's do that in the next step. 9 plus x squared minus 6x times 1/2 is now going to give us 49 equals 9 plus x squared minus 3x. That's not a bad equation. It's a quadratic, but this one doesn't use the quadratic formula. This will be a quick one to walk through. I'm going to start by putting 0 on the left-hand side, subtracting 49 from both sides. But first, I want to put it in order, so I'll put in x squared minus 3x. Now take this positive 9 minus 49 to give us a negative 40. And this one factors in a nice clean way. It's 0 equals an x plus something, an x minus something. And great choices with 40 are things like 5 and 8, right? We can put in maybe positive 5 minus 8. That'll give us our middle coefficient of negative 3. But thing to observe about x, it's always a positive quantity. So even though this equation implies two values, negative 5, positive 8, we'll throw away the negative value. So we'll have that x equals 8 inches. So at the angle of pi over 3, and it looks like it really was drawn to be pi over 3, we're expecting 8 inches going this way. So we have two values that we have to plug in, the pi over 3 right here, and the 8 inches that we found right here. Any questions so far, folks, to that stage? Okay, now that we have those values, we come down over here and we're just going to differentiate this equation with respect to time. When we do that, we have to be extremely careful though. X is not an ordinary variable at all. X changes with time. So here's our reminder for walking through this with implicit differentiation. X is some function of time. And what's also weirder is theta. Or where did we put that? Oh, right here. Theta right here in green. That varies with time. In fact, we indicate a derivative with time, and so did they verbally. So theta is some other function of time. That means when you go to differentiate at x squared, that's a 2x dx dt. It's a chain rule right away. And same with cosine theta. We'll be real careful with that cosine theta because it definitely looks different. So let's give this now a full try and try to get through this. I'm first going to clean up this equation a little bit and just subtract 9 from both sides. Not much of a cleanup. We get 40 equals. Then I'll give it a little bit of space and go x squared minus 6x cosine theta. Oh, this is worse than I realized. There's a product rule hidden in there as well, that 6x and cosine theta. So we'll deal with that as well. Now differentiate with respect to time on the left-hand side and the right-hand side simultaneously. So now we're in the land of taking the derivatives both with respect to time. I'll go first. The derivative on the left is 0, and we're well on our way, halfway done, right? We just need to do the opposite side, but it gets a little bit tricky. Derivative of x squared, just like what we did when the person was walking east and walking south. There's an outer power of 2. That's the outer function. We first differentiate it to get a 2x, now to power 1. Then we differentiate the inner function, x, which varies with time, and write times dx dt. Now right here, it becomes an adventure. We have a product rule. I'll put a multiplication right here just to be specific. Now, there's a couple ways you can do this product rule. Sure, it starts with a negative, but you could organize like this. Plus, I want to differentiate to negative 6x first and copy cosine theta. So I'll write cosine theta times the derivative with respect to t of negative 6x. And just in case this becomes a conflict, let me put a border right here. Now, on the next step, I'm going to copy the negative 6x. So I'll go either plus negative 6x or minus negative 6x if you prefer. You can just drop that plus. But for seeing the product rule, I like to include that plus in the middle. Only reason I do it that way. Then differentiate the cosine function with respect to time. So times d dt of cosine theta. Hey, that actually kind of fit, but we'll keep that border right here. So all I've done so far is right here. Let me use a different color so we don't have yellow everywhere. It starts to lose its meaning. Let's go with orange. All of this turned into all of this through the product rule. Is that readable? Okay, that look all right to folks for readability? Okay, sometimes these colors don't combine in a nice way. They look nice on my projector, but they could be bad up there. Just let me know if they don't look well and we'll change it up. So I highlighted in orange just to show we're doing the product rule at those stages. Now I think we're ready to just finalize this problem. On the left, we have a 0 equals 2x dx dt. Now through the product rule, this is going to turn into plus cosine theta. Now over here, we're taking the derivative of a negative 6x. That'll turn into negative 6. The derivative of x, we have no idea what it is. It's an unknown function. Exactly. So we put in negative 6 dx dt. On the next step, I'm going to drop these parentheses and put the negative 6 in front, wiping out the plus sign. Then here, I'll drop the parentheses now and just call this negative 6x. Right here, let's be very careful with that cosine function. It's a chain rule once again. So we'll think of cosine. Would that be the outer or the inner? Good call. That one is the outer function. We'll take care of that first. Now theta, right here, that one is inner. We don't know its derivative. It's some unknown function like we indicate up here. So when we go to calculate the derivative of theta, we'll just call it d theta dt. There's not much more we can say really. So let's run through that last step then. So I copied in the negative 6x. Now differentiate cosine. What kind of function would that turn into? Is it positive or negative sign? Good call. It's a cofunction. It's got to be negative. That means I need more parentheses because I can't put a negative without saying I'm subtracting, but I'm really multiplying. So parentheses here, just to be careful. Cosine turns into negative sine. Theta goes inside as the inner function does, unchanged. Then we multiply by d theta dt. That's the derivative. Oh, I wrote some weird things. I said inner, but I should have said 2 there, not 1 again. Sorry about that confusion on that. Okay, so what I've done is taken the derivative of cosine, the derivative of the inner function just becomes d theta dt. So there it is, all of it in its huge mess of a glory. Let's remind ourselves what we were even doing. It's really easy to lose track. We want to find the rate of change of x when theta is pi over 3. In other words, we're finding the velocity of the piston if we do that. So we're getting really fat, really close. I'll put an arrow here just as a reminder. We're solving for dx dt. Can we do it? Well, we're doing it when theta is pi over 3. So we have a substitution here and here. So that's helpful. We also know that the rate of change of theta with respect to time is 400 pi radians per minute. So we have a value right here we'll throw in. There's more. We know that x is 8 inches. We ran through the law of cosines and solved for it. So 8 inches will go here. Let's see, where else? And here. So that's an organization of what gets substituted inside. Now let's make those substitutions. I'm just going to go left to right, follow the color coding, and we'll throw in those values. Twice x is twice 8 to start. Then dx dt is the thing we're solving for. We don't expect to do anything with it for the moment. Then it'll be plus cosine. Theta is pi over 3. And we've worked that before. Cosine pi over 3 is just a glorified 1/2 at this step. Oh, I forgot to move our negative 6 over. Darn it. Let me try that out one more time. I want to take this negative 6, write it in right here, just to make it more readable. Then do cosine of pi over 3. Then it still multiplies dx dt. But these are like terms altogether. I have 16 dx dt right here, and we'll have -3 dx dt's right here. So it's altogether 13 dx dt's. It looks weird, but it still combines as like terms like you would expect normally in algebra. Then over here, I'm going to change this up a little bit as well. There's double negation, so this turns into plus 6 times the value for x, which is 8 inches. Then it's sine of theta, so sine pi over 3. And then finally, we're multiplying by the speed at which the arm right here is rotating, which was 400 pi radians per minute. So times 400 pi. So it's all placed in. Our last thing to do is solve for dx dt. But also remember the reminder, there's so much stuff that happened on paper here that we need anything that we can get that might be any hint of a check partway through. If we're expecting a negative derivative, that's something we have at least. I don't have much more, unfortunately. So if we get a positive derivative, then it's back to the drawing board on this one. So let's work this out and see just what happens. In case we need it, here's the next page. I think we'll need it, but let's work this out as 0 equals. With the red dot, we're going to get 16 dx dt. Cosine pi over 3 is a half. So a half times -6 will give us -3 dx dt. Now up to here, we're at plus 48. But sine pi over 3, that turns into the square root of 3 divided by 2. So times √3 over 2 times the 400 pi. And I'll put just a notice here that this continues. Let's sort this off on the next page. So it's 0 equals, we can combine dx dt. You could factor it out and visualize 16 minus 3 is all that's left over. At the end of the day, it's 13 dx dt. Over here, we can divide 2 into the 48 and get plus 24 times 400 times pi times √3. I think we've got all those constants in play. 2 in here, giving us 24. Then we have a √3, a pi, and a 400. I put it together in that way just to show nothing else goes inside the square root here. So next thing to do is we're solving for dx dt. You would just subtract 24 times 400 times pi times √3 and then divide by 13. So the final step is we can say, therefore, dx dt equals, first I'm subtracting this, minus 24 times 400 pi √3, then divide by the coefficient of that derivative, 13. And I didn't put it in the calculator. Let's put it in the calculator and see what happens. I have a cheat sheet here because this problem scares me in case I lose my way. But for the calculator, here's what we're going to get. -24 times 400 times pi times the square root of 3. And, oh geez. That should work out by order of operations. Everything would multiply into the numerator. Just made me a little bit nervous. We're getting -4018.3. I think would be decent rounding. This was in units of centimeters per minute. So that arm, that, what they call it, piston, is absolutely flying at a rate of 4,018 centimeters per minute. But again, it's because it's an engine, we're expecting it. It was revolving at a rate of 200 revolutions per minute. So this should be going really quite fast. Really kind of a strange problem. But when you look at this one, think of it as really just a redo of this one. We just had to use law of cosines, and that was the nasty thing about it, which means we had to specify a theta value, and also something was rotating in our problem. which gave us the extra conundrum of having to write out that derivative in a pretty strange way. Well, any last questions, folks, about this problem here? Okay, we didn't solve the one with mass changing, but I'll place a solution on that one in the notes before it's completely finalized. Well, that's all we have for today, folks. If you have questions, I'll be happy to help. Otherwise, have a great night. Because it's an exam week, if you have questions over this weekend, please don't hesitate to email. I won't be at my computer all the time, but I will be checking it quite a lot. And I'll be very happy to help out with any questions you have. Also, maybe another further reminder, coming back on Monday, my office hours are going to be in tab 268 from 4:30 to 5:30 p.m. Well, have a great day, folks. Don't work too hard, but if you are working and you have questions, don't hesitate to reach out. Thank you. Thank you. How's it going?
I have a question on my 18.
Sure.
Did I do this right?
Let me take a look.
Because you said that this would just convert to just T.
Yeah, when you take the derivative of a natural log t, it just turns into 1/10.
Number two,
Yeah,
okay,
the
yeah, I
LF
saw that in my
goes away.
notes again, but I just want
Gotcha.
to make sure that's right now.
So let's see here. We've got natural log t, so that derivative is 1/t. This one, t squared plus 1 comes down. You have to multiply by 2t against the 4, so at looks good.
Okay,
Here we've got -1/3. So we're in good shape with the negative sign. 2t minus 1 comes down. We'll multiply by the derivative of that, which is 2. So that's why you have a -2/3 right here. Yeah, that looks great. You've got it.
okay, so then that would be my answer.
Absolutely, yeah.
Okay, and then I have a question on part B of 22.
Gotcha.
I don't know where would I plug in 10,000? Or 20,000?
You want to plug in 20,000 first.
Okay, so would I plug it in, I'd plug it into R,
Yeah,
and then what would I do after that?
you would set it equal to -2. They said when the radius was 20,000, the force was decreasing at a rate of 2 newtons per kilometer. So set it equal to a -2 on that side.
So, would I still have this?
Yeah, your goal is to solve for G little m big M all together.
Oh, okay. And
Once you
then
have that value, you plug it back into part A and plug in 10,000
for part
after
A,
that. Yeah,
right. Okay, so I do that,
Mhm.
and then I would multiply for this side, divide by -2, and I would plug that into this
Exactly.
times 10,000.
And, or 1 second.
So I
Oh, wait,
get this.
Well, this is your derivative here. Sorry, I was looking at
Okay,
the
no,
wrong
you're
step.
good.
So you're on the right track. You're
Okay.
solving for G little m big M,
Okay,
but then you put it right here
okay,
because this is your F prime on this step.
yeah,
So on your F prime, the problem is solved once you replace this with its value from that equation.
yes,
And when you put 10,000 inside.
that's my answer for B.
Exactly, yeah.
Oh, okay, I'm going to solve that.
Sounds good.
I have a lot of questions, so.
Sure, we can go back and forth.
Okay,
How
I'm
about
gonna
we'll
be
do
on-
yours, then we'll do yours and just keep going back.
Well,
and
let's,
forth.
see- I will see if we even have any questions that actually line up first.
I'm gonna be honest, I understood like none of 3.7,
Mhm.
because I was doing my assignment, the assignment 5, so I was like, oh, F, and then,
Mhm.
yeah. So I understood like none of the homework problems. I got some of this one done,
Yeah, that looks pretty good so far.
but I just didn't get part B done.
So part B on this one, I like how you started. You have to put in 25 for the height. Then it'll be, let's see. It'll still be a T right here and a T squared right here when you plug that in. Because all you're doing is putting in the height of 25 into the original thing and finding 2 time values. Now you have to solve this equation for time. And after you do that, you'll get 2 answers for time and you'll plug them into your velocity function. That's what'll give you velocity on its way up and velocity on its way down.
So I plug them into,
Your velocity S prime or V of t.
this equation right here.
Yeah, that's your velocity there. So from here's the height. When you differentiate it, this is your velocity function.
Mhm.
Now you're finding two times when it's coming up and when it's coming down at height 25. And you plug them right back inside there.
How would I figure out the t if there's a t and a t squared?
This is one where you have to use a quadratic formula and use a calculator on. It's gonna be like approximated values, like, I forget the actual amount, like 2 point something seconds, 5 point something seconds. But you'll want to get 0 on one side, so it's in its standard form, then use the quadratic formula.
Okay. Quadratic formula, that's the. I know this one, wait.
I feel the same way sometimes. If I haven't used it in a long, long time, takes a bit of refreshing. This will never show up at an exam out of the blue, though. I would never do that to you folks. But while you're working on that, do you have a question we could take a look at?
Yes, I went through all this. I have no idea, even if I'm anywhere near right, but this is what I got through all these answers, and I'm wondering if I did this right.
Sure. So let's take a look at number 4. What section was this one in?
3.8.
3.8, number 4. Okay, let's take a look at that.
This is the one that's not even on the solution, so I'm basically just blind. I can't even check my answers.
Yeah, even problems are exciting in that way. So assignment number 6 is what I'm assuming, or wait, no, this is 7. You said 3.8, number 4. Gotcha. So here's our number 4.
Mhm.
Oh, we're doing the exponential growth on this one.
Yeah, I think I got that far. Because literally what I did with this one is I know this 2 minus the 6 would then make 4, and then you divide it by this, then you get that total answer, and that's the total answer for that.
This is actually a pretty complicated problem right here on part A. When we did this same question,
I think it might be a little off because I think 400 would technically go right here then. If I remember right.
so the bacteria was 400 after 2 hours.
Yes.
So let me just put this out of the way over here. We could write that out as saying,
But this is what I remember because this is like that's the final answer for A. It's the natural log of 640 divided by 4.
but how did you get there?
Well, I divided it by this much and I got this much, and then I just divided it by 4 because of that, and then natural log it.
I don't know if that necessarily would work on every problem, though.
That's what I just used because that's what you did in 3.8, and it's supposed to think with one with matches the bacteria one.
Well, let me
So
show you what I
basically,
did in
I
3.8.
transferred it over to,
In 3.8, it was almost the same question. Bacteria count was 600 after 2 hours,
Mhm.
75,000 after 8 hours. But we had to start off by doing this. The
Yeah.
world population size at 2 hours is 600.
yeah, that's why it's right there. 2 hours is 400.
But then we had to go down to this step. P at 0, either the K times 2 equals 600 is our
That's where I
net.
got the minus 2 to the 6, which then would make it 4.
Gotcha. So you've got a value of 4.
And then I divided it by 6, which if you divide that by 600 would equal that, and then you divided it by 6 with the natural log, which then would equal this. And that's how I got that answer. I just skipped the steps in the whole and did them in the, because I knew what I was doing. I was like, okay, you do this, and then a kind of basic outline of what I was doing. To get out to, this is the total answer.
Gotcha. Huh. I'm not sure that method would work on every single problem, though.
No, I just used it on the bacteria one because I matched the bacteria one. So I was like, okay, I guess those ones do match. I guess they'll work. And because it also followed the line of it started with 600 and after 2 hours, and then at this hour I did it with this one. So technically, that's how I applied it to this one because it had the exact same question wording. So say if a different question, say it said, instead of said, like, it started off with 300 cells after 1 hour, and then about like, say, 12,000 cells after like something hours. I would apply the same method to it because it's the same lining up the same method of hours. And And that's why I struggled with this one, because even with the one, there was no one I could have found this to compare it to, so I kind of got stuck on it.
Gotcha. Well, let's keep on thinking about this problem number 4 right here.
I'm just wondering if I even did any of the calculations right at this point.
It doesn't look right on face value, but I mean, I could go through the motions and we can see if we agree.
Yeah, because that's all I'm wondering here.
So let's take a look at this. If I was to start off this problem, it says bacteria count is 400 after 2 hours. So I write population size at time 2 is 400. Then 25,600 after 6 hours. Population size at 6 hours is 25,600. But then we use this equation. Population size at any time t is the initial population size times e to the power kt. So that's pretty much how we started our problem. Then we come back over here. If population at time 2 is 400, then that means we can say,
1 hour equals 200 basically.
well, I would write population at time 2 equals, we're putting a 2 right here for time, so P naught. E to the 2K, 400 goes in to the left-hand side, P naught, E to the 2K. So that resolves that first equation. We do the same exact thing to the second equation over here for P at 6. So if we put 6 right inside here,
Gonna end up with yacht of E of 6. Okay,
exactly,
and then
then that value was 25,000 on the left, so.
and then it would be equal to 25,000 for that. And then you would basically do the whole motions, and then it would be. You would remove the 2, because then you would move it over to here, because then that would minimize the 2K, so it'd be 4K at that point. Because if we're going by the same rule, it would minus this to minus that, or technically, I don't know what you did, but I just know it went over to here. You need to minus the 2 tops because the 2 towers couldn't mix it, so you just cross out this minus that, which then would be 4K.
But you've got to show those steps on your work.
And that's the problem where I struggle with your work. I have this method of where I see connections and I just skip over them because it's better for me to fly through that. And I do that in a method because if I do that, I can do that in test setting, I can save much more time. And that's where I get this from. And this is the problem I always have with math teachers, is that they don't agree with me on this whole skipping
Well, it's
method.
not that I don't agree with you, but if you're not sure if that's right, then you don't have enough detail to convince yourself.
Well, then I can.
You've got to
I
be
can-
convincing yourself that you've got
So-
the right answer.
At this point, then, if you want me to do that this way, I can write it like instead of like this. I can do 2K. Okay. That way I can say it's minus the 2K. And then I got 400 for one side, and then another one for 2, 5, 600 for the other side. And then I would minus that to 4. Okay. Then I would divide those two by 200. 600 divided by 100. Then that would equal out to 640 of 4.
That'd be just right.
Let me take a look. So -15 plus or minus the square root of. This should just be a 15 right here, rather than a t. So it'd be the,
Oh, do I not add the variables?
no variables inside here, yeah.
Oh, okay. Get rid of these.
And
So on this part A, you're solving for, when it says relative growth rate,
Mhm.
you're trying to say what K is equal to altogether.
yes,
So what was your value for K on this one?
well, technically, if this
This
as a
right here.
whole, I would need my nice good calculator because that's a good, actually. does
But
my
it's
answer calculate?
really this right here.
Yeah, it's technically, this is the answer.
Gotcha. And the work, you're taking 6K minus 2K. And I can see why you would do that, but the reason for taking 6K minus 2K is because you want to solve for P naught. it'd be 400 over e to the 2k. Right here's a p naught, so we can substitute and say 25,000 is equal to 400 e to the 2k times e to the 6k. And it's here to here where 6k minus 2k come into play.
And that's where you remove it, that.
400 e to the 4k. So yeah, you should be getting a 4k right here.
Mhm.
And your 640, that came from the 25,000 divided by 400. So we
I
get,
did check with that, my calculator.
awesome, yeah. So 640 equals e to the 4k.
And this is why I got like a decimal here, because I like all of this and then e to like, I think it's 2 times all of that. Literally all of this right here, you throw down here. And then you do the base form of that, which would be 400. Because the bacteria of 2 hours is 400. And then that would equal up to this much of a rate.
Mhm. But do you see what you would do next, right here to solve for k?
You would take that and then you would divide it by 4. And that would also transfer this
But
into
there's a step in the middle that tells you why you're dividing by 4.
what is this?
You have to take the natural log of 640. Take the natural log of e to the 4k,
And natural. log
and those
cancels out.
cancel. Yeah, so you have natural log 640 equals 4k. And then finally divide by 4, and that's your quantity k.
Okay, that makes sense.
Yeah,
At least now I understand why he is there.
yeah.
But yeah, I just understood that once you get here, you just divide that by 4 or whatever. So even if it was 3.5, then I would still have to divide by 3.5.
Mhm.
That's all I understood. I saw connections, I saw coincidences. And if the coincidences lined up for me, my brain can say, okay, this just does this.
Sounds good. Well, question over here, Stephanie, and then we'll go back to UC Lee.
I'm having trouble with this one. I don't know, cause I got a decimal.
This 20,000 right here. So, hang on. You would have, it really started off like this, right? So we're solving for that equation.
Yeah, for that,
But-
and then I multiplied by 2,000, 20,000.
But this denominator 20,000, it's raised to power 3. So I think that's why it's getting a little mixed up in there.
So then what I raise the power to 3 and then multiply by that?
Technically, it would be.
To
negative
power
3.
3 right there, yeah.
Wouldn't it technically be -3 as well?
There would be a power 3 on this one.
So do a power of 3 there,
Yeah,
and then those would cancel?
they would cancel, yes.
Why was
Okay.
mine a -3?
And then,
You brought it up to the numerator.
so then this would be power of 3,
Yeah, exactly.
okay. Let's see if that fixes my problem.
Sounds good. How's it coming over here?
So then with this, would I just plug in this, but instead of being positive, it'd be negative, and then I plug that into here.
Yeah, but what you want to do is get like 2 decimal answers. So you want to throw this into a calculator, approximate, see what they end up in, and then you throw it inside the velocity function. Sorry, they would go back up in here.
Okay,
So that'd be your velocities you're getting.
okay, never mind, okay, I made a calculator.
I think I might have one if you need one.
Here,
Here you go.
Thank you.
It's not the world's friendliest calculator, but it is one.
it's quite similar to mine, but I think mine might be a little bit newer.
Yeah.
Anyway, as I was saying, I got this far and then I kind of stopped because the next step made me confused. Because I don't even know if this is the right answer, because I think you would want me to put down to the 10th place, so instead of 15 point all this would be 15.81.
Yeah, you can use any reasonable rounding. So what makes sense in the problem?
And
go ahead
this is
round
where
it.
I got stuck for this one.
On part, you're saying,
Yes.
find the growth rate. So the formula for growth rate,
And the problem is, instead of going to a decimal, it went higher, it went to like 3,000 and something above what it was getting right here. So I was like, okay, that's not working. So I was like, it went to like 30,000. So it went above to what it was. So I was like,
That's possible, actually.
It is possible.
It is, yeah, because they grow so fast. Even if the population was 22,000 at one instant, the rate at which is increasing can even exceed that.
So
That's kind
technically,
of wild, isn't it?
so technically, this is just the rate of something happening to it. Well, this is the actual rate of how it is growing.
Yeah,
Okay,
so this is the amount, but not the rate.
okay, because I was like calculating, I was so confused. I was like, shouldn't this number be lower? Because it should have been more like a reasonable. I would understand like 500 point something, something. But
Mhm.
30,000 of this does not make sense.
Yeah, well, the formula you have to use. It sounds like you probably have the right value. it
I
just
did, I
looked
did, I
weird.
used the right formula. I just like, because you're supposed to do like something with the natural log or something. I remember that.
It's really just this. You
Yeah,
take
Still don't
the
know that.
growth rate, K, that you solve for, and you take the population size at time 4.5.
So K is that natural log this.
Yeah, the thing you solve for right here, relative growth rate.
Yeah, so it'd be natural log. Well, first, you're gonna have to. Right. Natural log of 640 over 4. And then you want me to times it or divide it?
Well, you'd have to times
Oh, yeah,
through that
times-
formula.
4.5.
Well, no, it's
No, oh, yeah,
the
it's-
population
it's that,
size at
it's this.
4.5. Yeah, exactly.
And then, and yeah, that's where I got confused because this is when I put it in. 4 point, I'm just gonna decimal it out. Right. Oh, no. I don't know if that's a 4, 9, or 6.